In the previous videos, we have shown you how to apply the rules of inference to build na valid arguments on compound na propositions. Now, the question is how we can use quantifiers with the rules of inference. So there are also several na rules, actually 4 na rules of inference for quantifiers, and let's move on to the first one. So the first one is the universal instantiation, or the UI. So we have this form: for all x, p of x, therefore p of c. So this is the rule of inference to conclude that p of c is true where c is a member of the domain, given that the premise for all x, p of x is true. So in other words, if this premise is true, wherein for all x, p of x, so that means that for any member of the domain, for any member c of the domain, then the p of c is true. So if you remember, the for all x, p of x, and we can express it via a conjunction, wherein we have the p of x sub 1 and p of x sub 2 and until p of x sub n, right? So we have, in order for this to be true, then it requires that every member of the domain x should be true. So we can say then that, or we can then assume that this p of c is true given that this is true. Okay, because this will only be true if all or each of this member of the domain in the predicate will be resolved to or evaluated true. Okay, so suppose we have the statement, all dogs are cute, therefore his dog is cute. So again, we can convert it into its argument form. That is, the arguments will be converted into using propositional variables. So let p of x be x is cute, wherein the x belongs to the domain all dogs. So the all dogs are cute may be written into its predicate form for all x, p of x, wherein the domain of x is all dogs. Therefore, the p of his dog should also be true, given that the premise all dogs are cute is true. Okay, so let's have another law. We have the universal generalization, or the UG. So we start with this premise, p of c for an arbitrary c, therefore for all x, p of x. So this is the rule of inference that states that for all x, p of x is true given that the premise p of c is true for all elements c in the domain. So in other words, we have, let's say, the p of x sub 1 and the p of x sub 2 and until p of x sub n, right? So if this will all result to true, then we can say that for all x, p of x is also true. All right, so we have this example. Suppose let C be any student, and the student C has a personal computer. Therefore, all students have a personal computer. So let P of x be x has a personal computer, wherein the domain of x is all students. So we have this premise, P of C. Okay, therefore, for all x, P of x is true, given that the P of C is true, wherein the C here is actually an arbitrary element of the domain. All right. And then we also have existential instantiation. There exists x, p of x, therefore p of c for some element c. So this is the rule that allows us to conclude that there is an element c in the domain for which p of c is true if we know that there exists x, p of x is true. So do you remember again that there exists x, p of x can be written in the form of disjunction? So for instance, we have p of x sub 1 or p of x sub 2 or until p of x sub n. And suppose that this is true, then we can say that either this or this or this element C in the domain for which P of C could be either true. So if this, suppose this is true, then regardless of the value of P of x sub 2 or the other elements in the domain, then this will be true. Okay, so we can say that again, if this is true, oops, if this is true, then we can say that there is some element C in the domain which could make this P of C true. Okay, so suppose we have this example. There is a person in the store, and therefore some person C is in the store. So we can express it in the predicate form, predicate logic na form. We have that P of x be X is in the store wherein X domain is all people. Okay, so we can express this using this notation or symbolic na form. So there exists X P of X, or in its natural language form, we have there is a person in the store. Therefore, P of C, wherein C is some element in the domain. Okay. Now we potential generalization E of G, wherein for B of C, or there is an element C for which P of C is true. So therefore, this universal quantification, there exists X, P of X, is also true. Okay, so if you remember, we can express existential quantification in the form of disjunction. So we have, let's say, P of x sub 1 or P of x sub 2 until P of x sub n. So we can say that if at least one of this is true, let's say all of them are true, then there exists X, P of X should be true. Now, suppose we have only one C which is true and the rest are false. Still, this will result to true because we only need one. Suppose this is also true. So, and we have a false, false P of C. Then still this is true. Okay. So again, if there is just some element C wherein which P of C is true, then we can say that this, or we can generalize that this existential quantifier is true. Okay, suppose we have this example. His dog is playing in the park, and therefore there is a dog playing in the park. So this is supposed to be, sorry for this mistake, we have X is playing in the park. Okay, so we have the domain of X is the all dogs. So we have this premise P of his dog, or if we plug that in the P of X, that will be his dog is playing in the park. And then therefore, since this is true, then our existential quantifier is also true.